Hello everyone, and welcome back. Today we're going to continue our exploration of set theory fundamentals and talk in particular about relations and functions. Last time we talked about some properties associated to sets, such as the cardinality, partitions, power sets, and so on. Today we're going to introduce the concept of relating two or possibly even more sets to one another. So let's assume that we have the set A, which has the elements 1, 2, and 3, and the set B that contains the elements A, B, C, D, and E. So what we would like to do is define what we call a relation between the sets A and B, and we're going to be denoting this by subscript A or subscript B. So there's many different ways that we can define a relation between these two sets A and B. And when we say relation between two sets A and B, that means we want to develop a relationship between the elements of each of these sets. So let's assume, for example, we want to relate the sets A and B in the following manner. In particular, we want to say that 1 is related to A, we want to say that 2 is related to B, 2 is related to C, and let's assume that 3 is related to D. And let's also assume that there is no element in A that is related to B. So we write this in set notation as A related to B. So a relation is, of course, a set, and it's going to be a set of ordered pairs because we have an element in A and an element in B together. They have a relationship, and we call that relationship an ordered pair. So 1 is related to A, so we write that as 1 comma A. Then we have 2 comma B, we have 2 comma C, and we have 3 comma D, and that is the relation ARB. So therefore we can say that little x r little y is a relation between elements x and y. So i.e. x belongs to A is related to y an element of B, right? If the ordered pair xy belongs to the set A R B, right? So that's a basic outline of what a relation is. So can you give me an example of an element that does not belong to the relation ARB? So you should be able to see that, for example, 1B does not belong to ARB. So this is a fancy way of saying that 1 is not related to the element B. Now that does not, of course, imply that you can't define a relation between the elements 1 and B via another relation, but for this particular relation there is no relation defined, at least. So let's sort of build on this concept of relations and introduce a couple other notations. So keep in mind, let's assume that we're working with a relation A, R, B. So the set A is referred to as the domain of the relation R, and we're going to be denoting this by DOM of R. The set B is known as the codomain of R, which we're going to be representing as CODOM of R. So what exactly is the domain of a relation? So the domain of a relation is going to be the set of all values that we can match from and the codomain is the set of all values that we can match to. Emphasis on the verb we can, not we do. Right? So if we look at our set A, B, C, D, A, B, C, and D, and we sort of look up back to how our relation was defined, notice that ABCD, which is a subset of the codomain, which is the set B, includes all of the values that are actually mapped to. And notice that element E belongs to the codomain, but it doesn't belong to the set of values that we're actually matched to from elements from the domain. So this is another concept that we're going to define. So obviously this set is a subset of B. And for this particular example, this set here is called the range of the relation R, which we're going to be denoting by RAN of R. And the range of R is the set of values that are matched to from at least one element in the domain. So that we are matched to versus that we can match to. So that's the difference between, for example, codomain and range. Obviously, knowing the range of a relation is definitely a lot more useful than knowing the codomain of a relation. Codomain is like, I allow my values to be in this set, whereas the range is like, okay, these are actually my values for this particular relation that we are actually mapped to. Let's look at another example to sort of bring these things together. So let's assume that we have the set of integers, which is again represented by z. So this is going to be the set consisting of, for example, -2, -1, 0, 1, 2, all positives and all negatives above and beyond. And let's define a relation between this set and, for example, again, the set of integers z, but I'm going to write them a slightly different way. I'm going to write them as, for example, -1, 0, 1, 2, 3, 4, 5, and so on. So obviously all these integers are there. So what I want to do is I want to define a relation R between z and z. So I'm defining a relation between z and z. So z is going to be the domain, and z is going to be the codomain. And you won't be able to tell me the range unless I actually spell out what this relation R is actually equal to. So I'm going to define the relation R via the mapping. I'm going to take a value x in my domain, and I'm going to square it, and I'm going to send that to the element in the element z. So I'm going to map x to x squared. I guess that's a better way of writing it. So I'm going to take x in the domain, and I'm going to map it to an element in the codomain that is going to be the square of the value in the domain. So for example, if I look at this, -2 is going to be mapped to 4. -1 is going to be mapped to 1. 0 is going to be mapped to 0. 1 is going to be mapped to 1. 2 is going to be mapped to 4. 3 is going to be mapped to 9. -3 is also going to be mapped to 9, and so on. So let's actually list a couple of the values in this particular relation R. And some people, if you're only talking about one relation R, some people will just represent that by R. So if I pick the element 0 in the domain, that's going to be mapped to 0 squared, which is going to be equal to 0. If I pick the element -1 in the domain, that's going to be mapped to 1. 1 is also going to map to 1. -2 is going to map to 4. 2 is also going to be mapped to 4. 3 is going to map to 9. And if I pick, for example, -5, that's going to be mapped to 25. And there are several other numbers that I could pick in here. For example, I could pick, for example, -8. That's going to be mapped to 64. If I pick 9, that's going to be mapped to 81. And there are, of course, infinitely many other values that are located in this set. So if I try and construct a Cartesian graph of these values, so let's assume I pick an element x located in the domain of my relation, and then y is going to be associated to all of the elements in the range of my relation, then what do I have? Well, I have 0, 0 located there, I have -1, 1, and 1 located there, and I have -2, 4, and 4 located there. So 1, 2, 3, and 4. And if I were to extrapolate these points, then I'm going to have, for example, this U type of behavior, right? But nonetheless, this is what we call a discrete graph because the points are not themselves connected to one another. So if we extrapolate these points, we get what we call a continuous graph, which is another or fancy way of saying that there's no gaps between points. And we'll introduce a more formal way of saying continuous a little bit later rather than this vague description of what it means to be continuous. So let's look at a discrete representation of relation again, just to make sure we understand this. So let's assume we define, for example, R1 to be the relation given to be 5, let's do 5, 3, 5, 3, 5, 4, 5, 7. And let's define another relation. Let's call it, for example, R2. Let's assume that this is going to be equal to 5, 3, 2, 4, and 6, 4. So for these two relations, you should be able to tell me quite a few things. For example, for R1, what is the domain? So for the domain for R1, the domain is obviously just going to be the element 5, and the range is going to be the elements 3, 4, and 7. So if we define R1 via this, then we have, for example, that different type of diagram. And if we look over here for R2, so we have again the domain, which is going to be 2, 5, and 6. And if we draw the graph of R2, which consists of the elements 3 and 4, notice that 5 is going to be mapped to 3, 2 is going to be mapped to 4, and 6 is going to be mapped to 4. So that's the graph of the relation R2. Just some qualitative things that you definitely should be able to see in this particular picture. So at least one x in the domain of a relation goes to more than one y in the range of the relation. So if we were to look at the Cartesian graph of this, and look at, for example, 5, obviously we have 3, 4, and 7 as the outputs, and we put a little dot. Notice that if we draw a vertical line through this, it's going to pass more than one point. Some people will refer to this as the vertical line test, or VLT for short. So at least one x in the domain goes to more than one y in the range. That is, the vertical line that you draw at x is equal to 5 is going to pass through more than one of these green dots. So what we usually say about this relation R1 is that R1 is not a function of x. And some people also put the adjective univariate function to emphasize that there has to be exactly at most one point that a particular x value in the domain goes in its range. And if there's more than one value for which a domain value gets mapped to, then we say that it's not a univariate function of the variable x. Now, we can make similar observations about, for example, R2. So each x in the domain of the relation R2, and for example here where we're talking about R1, goes to at most one y in the range of that particular set. For example, 2 goes to 4, 5 goes to 3, and 6 goes to 4. So if we were to, for example, draw our Cartesian graph, our domain elements are all positive, so I don't need to really emphasize on the negative side. So for example, 2, 5, and 6, and we're to, for example, go to 3 and 4. So if we were to graph each of these points, so 2 goes to 4, 5 goes to 3, and 6 goes to 4. If we were to draw a vertical line at each of these domain values, notice that those vertical lines will only cross that relation exactly or at most once. For example, if we draw a vertical line at 3, again, notice that it does not cross at most once. In particular, it crosses no times at all because it's not in the domain. So, is R2 a univariate function of our variable x? The answer is yes. Therefore, we can say that R2 is a univariate function of the random variable x. Some people, and I see often some textbooks even, will leave off this of x statement there and just be like, well, if it's a function, it must be with respect to the x variable. That's not necessarily the case, and this distinction is definitely extremely important once you start talking about multivariable functions. Now, this was the case, and we were easily able to see if it's a function of the variable x, given the discrete set representation of the actual relation, but technically you don't need to be given the set relation at all. For example, you could be just given a graph of the relation. For example, let's assume I have this continuous graph given as such. Let's call this, for example, relation 3. Is this a function of the variable x? So if we were to draw a bunch of vertical lines here, notice that for any vertical line I draw, it crosses at most one time. So therefore we can say that R3 is a function of the variable x. And let's draw another graph. Let's call it R4. Let's assume that, for example, this is R4. And let's assume that the horizontal axis is x, of course. So if we were to draw some vertical lines here, so notice that this vertical line crosses at most once, this at most once, this at most once, this at most once. But notice that once I start attacking these particular x values, it crosses 2 or possibly even 3 times. Notice here it's once again. So for a relation to be a function of the domain values x, it must be true for all values in the domain, right? So since there are some values in the domain that map to more than one element in the range, then we can clearly see that R4 is not a function of the variable x. Now, could you also say something about functions of y's? And the answer is, of course, yes. So for example, if I consider horizontal lines, for example here, this horizontal crosses once, 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 and notice that these lines cross more than once, so we clearly see that R3 is not a function of y. Some people refer to this as the horizontal line test, or HLT for short. And if we draw horizontal lines for this relation, for example R4, notice that all of those horizontal lines cross at most once, so we see that R4 is a function of the variable y. And those are some of the basic definitions for functions of x's and functions of y's via both the set and the graph notations of the relation. Now that we have the basic understandings of what a function of x and a function of y are, now let's introduce the more formal definitions of what it means to be a function of x or a function of y. So let's assume that we have a relation given by x is related to y, where x is generally speaking the domain and y is generally speaking the codomain. But let's assume that the domain and codomain are both equal to y. So the domain of R is x and the range of R is y. So we say that the relation R is a univariate function of x. Some people will just say a function if for each element in the domain there is at most one element in the range such that x is mapped to that element in the range, i.e. x is related to y. And similarly, if a function for each satisfies the property that for each y in the range, there is at most one element in the domain that maps to that element in the range, then we say that that relation is a function of y, and some people will also say that this relation is what we call one-to-one. So let's look at a couple graphical examples and sort of see if we're able to see whether they are functions, or functions of x's, or one-to-one, i.e. functions of y's. So let's assume that we have this particular graph. Is this a function, i.e. a function of x? So let's assume that x is on the horizontal and y is on the vertical. So if we were to draw a vertical line, notice that any vertical line we will draw, it crosses at most once, so it is indeed a function. But if we were to draw some horizontal lines, notice that it crosses more than once at some values in that particular range, so therefore it is not one-to-one. So let's draw another graph. Let's assume we sort of rotate this thing. Again, let's assume that's x and that's y. So if we were to draw vertical lines here, so vertical, 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 some verticals there cross more than once, in particular 3 times. So therefore this is not a function, but if we were to draw some horizontal lines here, notice that regardless of the horizontal lines we draw, it does pass at most one time, so therefore that is one-to-one. And let's draw this relation here. So let's again assume that this is the x and this is the y-axis. So if we were to draw some vertical lines, notice that any vertical line we were to draw, it crosses at most once, so therefore it is indeed a function. And if we were to draw some horizontal lines here, notice that those horizontal lines also pass at most once, therefore this is indeed a one-to-one relation. Let's draw let's draw a familiar object. Let's draw an ellipse that's sort of rotated sideways. Let's again assume that this is the x and this is the y-axis. So if we were to draw some vertical lines here, notice that those don't pass any, but these pass twice. It passes once somewhere along there. It doesn't pass any there, so therefore this is not a function. And notice these horizontal lines do not pass at all. That horizontal line passes once, twice, 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 once, and none at all. Therefore, this is not one-to-one either. So therefore, those are some graphical relations of relations that are functions, are not one-to-one, and any permutation of those classifications of one-to-oneness and being a function of the variable x. Another common problem that a lot of people encounter is how to find the largest possible real value domain and range of a given relation. So if I were to choose the largest possible domain, what is that domain that I could choose? So let's look at a couple examples to sort of see what I'm referring to here. So let's assume that we have the relation little x is related to y, provided that y is equal to x squared plus 5. So if we were to plug in all of the values x in the set of real numbers, would we get a real number back? So for example, I could choose some negative numbers, so negative numbers squared will be just positive real numbers, and I can always add 5 to those numbers. So literally any value of x, I can get a real number back again. So with this particular relation, one could choose the domain of this particular relation R to be equal to the set of real numbers. But it's not needed for us to choose all of real numbers. For example, we could just, choose 0 to infinity. So another way one could figure out, okay, the domain is, or what the domain of this particular relation is just plug in a bunch of numbers and plot them. So for example, if we were to plug in 0, we would get 5 back. So 0, 5 is an element of that particular relation. And if we plug in a bunch of numbers sort of surrounding it, we're going to get this particular different type of shape. So that's x, and again, that's particular y. So it's this parabolic U-shaped graph, right? So notice, if I were to graph all the points, it's also very easy to see what the actual range is. So again, the range is the set of all y values that I can obtain from elements in the domain, right? So notice that if I were to look at this and I ask you, is -7 in the domain? Obviously not, because there is no point for which that blue line crosses that red graph. And notice that there are actually no y values that are negative for this particular relation. 0 is not going to be in the range, 1 is not going to be in the range. The first value that is going to be in the range is going to be the element 5, and all elements above that is also going to be in the range as well. So if the domain of this relation is equal to the set of real numbers, then the range of this relation is going to be the continuous interval 5 to infinity. And we can see that just from the graphical representation of this relation. And once you become a little bit more comfortable with the most common relations, you should be able to look at an algebraic function and also be able to see what that actually is, right? But again, we do not have to choose the domain to be equal to R. For example, if I choose the domain of my relation to be equal to, let's say, -3, 2, and 1, then I'm only choosing a subset of my largest possible domain. So when I choose -3, I'm going to get some point there. When I choose 1, I'm going to get some point there. And when I choose, for example, 2, I'm going to get some point there. In particular, when I plug in -3, I'm going to get, for example, -3 squared is 9, plus 5, that's going to be equal to 14. When I plug in 2, that's going to be 2 squared, which is 4, plus 5, which is going to be 9. And then when I plug in 1, that's going to be 1 squared, which is going to be 1, plus 5, which is going to be equal to 6. So if I choose my domain to be -3, 2, 1, my associated range is going to be equal to 14, 9, and 6. So let's look at another algebraic relation and see if we can do the same. So example 2. Let's assume that we have the mapping x is related to y, provided that y is equal to 1 divided by 3x minus 5. And notice that for all of these things, notice that if we plug in a value of x on the right-hand side, we get one value of y on the right-hand side. So all of these are functions of the x variable x. And sometimes people will write this as f of x, and that's probably a more common way of notating this. Right? So therefore we can say that x is related to f of x, where f of x is a y value in the range, and this notation is again only appropriate if it's a function of x, which is why we write or read f of x. Right? Now notice that we are possibly dividing by 0. Because if we plug in a value for x, is it possible that we get 0 back? Well, what value makes 3x minus 5 equal to 0? Well, if 3x minus 5 cannot be equal to 0, that means 3x cannot be equal to 5, which means that x cannot be equal to 5/3. So the largest possible domain that this has, so the domain of R can be chosen to be the set of real numbers except for 5/3. And we can, of course, also write that in interval notation as minus infinity to 5/3, every number less than 5/3, and every number bigger than 5/3. Or R take away 5/3, that's also an appropriate notation. So again, we don't have to choose that domain. We could, of course, choose a subdomain. So we could choose the domain of this relation R to be equal to, for example, 1, 0, and minus 1. And obviously, none of those elements are equal to 5/3, so we're not going to be getting any issues. But if this is our domain, we should be able to easily see what the range of that is going to be. So if we plug in 1, we're going to have 1 divided by 3 minus 5, which is going to be minus 2. So that's going to be 1 divided by minus 2. If you plug in 0, we're going to have 1 over minus 5. And if you plug in negative 1, you're going to have 1 over minus 8. Now, question is, if I were to use the largest possible domain, what would be my range? This is not always obvious to see from the algebraic representation. But if we were to try and graph this particular relation in the continuous spectrum, again, you cannot have 5/3, so there is not going to be any value on that dotted line, but you should be able to see that the curve of this is actually going to look something like this, and it's actually never going to cross the x-axis. So if that is your particular domain, then one should be able to show that the range of that relation is going to be all real values except for 0, i.e. it's going to be all the values minus infinity to 0, union 0 to infinity. But again, sometimes those answers are not very easy to see from the algebraic representation of the function. You usually have to know a little bit about the actual family of functions that you're working with before you can actually easily see that just from its algebraic representation. Generally speaking, if the graph of a relation is already generated for you, finding its domain and range is typically a lot easier than if it were to just give you an algebraic representation of the relation and say what is the largest possible domain and range for which you can assign to this particular relation. Take, for example, this little looking ellipse in the Cartesian plane x and y, with x on the horizontal and y on the vertical axis. Let's assume that the minimum value that this ellipse attains is going to be equal to minus 7. Let's assume that its maximum value attains is going to be 2. Its minimum x value is negative 3, and its maximum value it attains is equal to 5. And someone asks you, what is the domain and range of this relation? So the domain is going to be, of course, the vertical elements. So I'm just going to be drawing a bunch of vertical lines along the x-axis and see when does it cross this particular graph. So if I were to draw a vertical line at, for example, negative 4, it doesn't cross the blue curve, so therefore negative 4 is not going to belong to the domain. So if I keep on drawing vertical lines, notice it does not cross until I get to negative 3. So negative 3 is going to be belonging to my domain. All of these values here are also going to be belonging to my domain because I'm crossing it. 5 is going to be belonging to my domain, but any value bigger than 5 is not going to be belonging to my domain since it does not cross my blue curve. So from this graph we can see that the domain of this particular relation is going to be the interval minus 3 up to 5. I'm going to do the same for my range. So let's delete all of these pretty little red curves that I drew. Right? Oh no, I deleted my ellipse. That's okay. We can draw it back. Let's come back. There we go, not as pretty as before, but that's okay. So how am I going to figure out my range? So I'm going to be drawing horizontal lines along my y-axis and see when it crosses. So notice that if I draw a line at 3, it doesn't cross, therefore 3 is not going to be belonging to my range. If I draw a horizontal line at minus 10 is not going to be belonging to my range because it doesn't cross. If I draw, for example, at 1, 1 crosses at least once, therefore 1 is going to be belonging to my range. And I can do this, for example, for all y values in between minus 7 and 2, and it's going to cross at least once, and any horizontal line out of that is not going to cross at all. Therefore, my range of this particular relation is going to be minus 7 to 2. And for all of these things, I'm assuming that there, of course, it attains that value there, it attains that value there, it attains that value there, and it attains that value there. Sometimes people use little open circles just to make things more complicated, but we can look at an example of something that looks like that in this next example. So let's assume that I have another graph, and let's assume that our graph takes a slightly strange looking graph. Let's assume that it looks something like this. Let's again put our y-axis on the vertical axis and x on the horizontal. And let's assign some x values here. Let's put minus 3 to be that value. And let's assume that 8 is that value. Let's assume that the y value of that open circle is 5, and let's assume that the y value of that closed circle is going to be equal to minus 4. So what is the domain and range of this particular relation? And let's call this relation, for example, R again. So again, you can draw a bunch of vertical lines here. So if I were to draw vertical lines at, for example, minus infinity up to minus 3, notice that I'm going to have a point associated to that graph. And if I were to draw a vertical line anywhere from positive infinity down to 8, that's also going to be belonging to my domain, so that's good. But notice I cannot draw a vertical line at, for example, 8 because that's an open circle, therefore it will not cross, but it will cross slightly to the right of 8. So we can see that the domain of this relation is going to be equal to, starting off left to right, so minus infinity up to minus 3, because that was a closed circle, so minus 3 is included. And then we're going to start off at something slightly to the right of 8 and go all the way up to positive infinity. So that's going to be my domain. And I'm going to do a similar strategy for the range, and you might want to pause this video to sort of see what that's going to be. So I'm going to start off at the bottom and work my way upwards, so minus infinity all the way up to minus 4 is obviously going to be included in my range. And then I'm going to go all the way up, but between minus 4 and 5, notice I'm not crossing that curve. Even at 5, I'm not crossing that curve because that's an open circle, but everything slightly above 5, it will cross. So therefore, that's going to be equal to 5 to infinity as my range, and that is the domain and range of this particular relation. Let's do just one more example just for fun. Let's draw it this way. Let's stay color consistent here. Let's do open circle and some slight curve there. Let's do a little horizontal piece right there. And let's do closed circle. Actually, let's not do the closed circle there. Let's do something slightly to the right, and then goes down, and then slightly up. All right. So this is our fun looking relation. X on the horizontal, y on the vertical as usual. Let's assign some x values here. Let's assume that the x value for this point is minus 9. Let's assume that the x value for this point is 7. And let's assume that the x value for this is minus 8. Let's assume that the y value for this is minus 10. The y value for that horizontal segment, 5. Let's assume that this point here is 11. And let's assume that for this little minimum point here, let's give that a height of 7. So what is the domain and range of this relation? And let's call this relation f. So you may want to pause this video and try this on your own. So the domain of the relation f is going to be equal to what? So we're going to have vertical lines crossing everywhere to the left of minus 9. So minus infinity up to minus 9. We actually probably need a little bit more room to write this. So the domain of f is going to be equal to, so minus infinity up to minus 9, and it's going to be a parenthesis because it's an open circle. We do not cross in between minus 9 and 5, but we do have some points from 0 to 7, and in particular we're talking about x is equal to 0, not 5, right? So keep in mind we're talking about x values here. So we're going to have a closed circle at 0, all the way up to 7, which is an open circle. Then we do not have any values between 7 and 8, and then from 8 onwards, notice that we're going to have x values associated to some values. So we're going to have 8 to infinity for the domain. All right, so that's allowing us to get the domain values. Now let's look at our range. So the range of this relation is going to be equal to what? So notice that we have y values underneath -10, but not including -10 because that's not a closed circle. So we have minus infinity all the way up to -10. Union. Then notice that we have this value of 5 here only, right? So we're just going to be including the number 5. And then notice that we do not have any values from 5 to 7, but from 7 upwards, we're going to have at least one value. We're going to have two values between 7 and 11, and one value for 11 and higher. In particular, that's just 7 to 11, and that's going to be closed circle. So 7 to 11, or just 7 to infinity, since there's no gaps in that particular range. And that's going to be the range of that particular relation. The next thing that I want to briefly go over, which is often associated to relations and functions, is known as horizontal and vertical intercepts, also often called x and y intercepts, depending on the label of the axes. So let's assume that we call the horizontal axis the x-axis, and let's assume that the vertical axis is the y-axis in this case. So the horizontal intercepts are often associated to the horizontal axis. So if the x-axis is the horizontal axis, then we're going to be calling these x-intercepts as well. Notice that x-intercepts, which are going to be these points that are circled in blue, notice do not have any height above or below the x-axis, i.e. the y value associated to them is always going to be equal to 0. Right? So in this particular picture, what are the x-intercepts of our relation R? There's clearly 3 of them, but keep in mind intercepts are points, and since we're in two-dimensional space, you should be giving me 2 numbers for each of these intercepts. So the first intercept is going to be -3, 0, then we're going to have 4, 0, and then we're going to have 7, 0. Similarly, one can find the vertical intercepts, and since the vertical axis is the y-axis, then these are also called y-intercepts. And notice that y-intercepts, which are the points circled in red, do not have any distance to the left or the right of the y-axis. Therefore, the x value associated to y-intercepts is always going to be equal to 0 as well for the x value. So notice that we only have one y-intercept here. Therefore, the y-intercept is going to be the point 0, 5. A couple of very interesting points that you definitely should be able to note are the following important results. So the first one is the following. If R, a relation, is a function of x, then it should only have at most one y-intercept. And 2, if R is 1 to 1, with respect to y at least, then it should only have at most one x-intercept. And you can sort of think about why that is the case. So if we were to draw a vertical line out along the y-axis, and it crosses at more than once, that means it would have more than y-intercept. And if we were to draw a horizontal line along the x-axis, if it crosses more than once, then it would have more than one x-intercept, and also be not 1 to 1. So this is just some of the basics. And it's very easy to see the x and y-intercepts if you're given the graph. Now let's consider a relation. In particular, we're going to say that x is related to y if x and y satisfy the equation, in particular x squared plus y squared is equal to 9. And eventually, one should know that the graph of this is going to be a circle, right? So let's see if we can find the x and y intercepts of this relation without actually generating the graph of it. So let's start off with the y-intercepts. So when we're looking for y-intercepts, recall that if a point is a y-intercept, then the x value is going to be equal to 0. So that's going to give us 0 squared plus y squared is equal to 9. And then we're going to have that, well, 0 squared is equal to 0, so we're just going to be left with y squared is equal to 9. From here, we can take the square root of both sides of this equation, and then we're going to have that the absolute value of y is equal to 3. And then there's two values of y that has an absolute value of 3. We're going to have y is equal to 3, and y is equal to -3. Therefore, what is going to be our y-intercepts? So our first y-intercept is going to be equal to 0, 3, and 0, minus 3 as our y-intercepts. Similarly, for the x-intercepts, when a point is an x-intercept, again, y is going to be equal to 0. Then we're going to have x squared plus 0 squared is equal to 9. Then we're going to have x squared is equal to 9. Then we're going to take the square root of both sides of this equation, and we're going to have the absolute value of x is equal to 3, which means that x is equal to 3, or x is equal to minus 3. So therefore, our x-intercepts are going to be equal to 3, 0, and minus 3, 0. So if we were to generate the graph of this circle, our x-intercepts are going to be minus 3 and 3. Our y-intercepts are going to be 3 and minus 3. Let's assume that this is the x and this is the y-axis. And if we were to draw a continuum set of points there, that would be the graph of our relation R. The last thing I want to talk about today with respect to the fundamentals of relations and functions is what is called axis and origin symmetry. Now, although there is some notion of algebraic symmetry, we're going to be focusing on symmetry with respect to the geometry or the graph of a particular relation. So let's assume that we have this particular graph here, and I'm going to be calling this relation R, that sort of looks like a discrete or a line and parabola based smiley face, I guess you could say. So does this graph have any symmetry? So if we were to consider the y-axis, i.e. we cut this smiley face directly in half, notice that everything on the right is exactly on the left, and let's assume that if this is drawn to scale, that is the same exact distance from the y-axis. So if this distance right here is, for example, 5, if this does indeed have symmetry, then this distance should be equal to minus 5. And the same thing can be said about these parts, and of course these parts as well. So this is what we refer to as having y-axis symmetry. So how can we represent this in terms of sets and relations? So a set has y-axis symmetry if xy belongs to the relation R and minus xy also belongs to R, then R has y-axis symmetry. And this has to be true for all x in the domain of the relation. So for example, if we pick this particular point here, which is for example minus 5, 3, notice positive 5, 3 also belongs to that relation as well. So let's consider an algebraic representation of relation. So we're going to say that x is related to y if y is equal to x squared plus 2. Does this relation, and let's assume that we're not going to go about it in the graphical way, does it have y-axis symmetry? So clearly, the set of points x, y satisfy this particular graph. So let's consider the point that is associated to minus xy. So minus x is related to y if and only if y is equal to minus x squared plus 2. So these points are exactly the same, and I'm talking about these points, provided that their algebraic relations are also the same as well. But keep in mind, when we square a negative number, we get the positive value as well. So this is also going to be equal to x squared plus 2, which is the same as x related to y. So x related to y and minus x related to y gives us the same exact y points in each of these worlds. And if we can consider the geometric structure, although we do not need to, and consider the graph of that, we should be able to see if we choose a point, for example, over here, x comma y, where that is positive x, and if we choose the minus x version and go up here, notice that the y value associated to that point is exactly the same. So let's consider another type of symmetry. Let's give a graph of this. Let's consider the relation whose graph is given to be this. Let's again assume that this is x and this is y. So if I were to choose an arbitrary y value, and that's going to be associated to some value of x. Now let's assume that I choose the same exact distance just in the opposite direction. Let's assume that this is, for example, minus y, and we're to go over here and then go up to that point. Notice that it has the same exact x value. So i.e. x is related to y and x is related to minus y. So in this particular world, we see that this is true, of course, for all x. Upside down a is shorthand for all. Then this is called what we call x-axis symmetry. X-axis symmetry. But notice if a curve does have x-axis symmetry, and it's the non-trivial x-axis symmetry relation, then if you were to draw a vertical line, notice that xy and x minus y usually are two different points, provided that y is not equal to 0, right? Then in that particular case, this cannot be a function of x if it has two non-zero y values associated to the same value of x. But of course, a special case is this relation here, where it's just the 0, 0 relation that considers the origin. Obviously, 0, 0 and 0, 0 both belong to the relation, so this has x-axis symmetry and also y-axis symmetry as well. So another type of symmetry that is often considered is what we refer to as origin symmetry, which sort of is a mixture of x and y-axis symmetry. So what I'm going to do is I'm going to draw a graph of such things. That's not a really good graph. Let's assume that it looks like this. Let's assume that this is our relation R. Let's assume that this is the x and this is the y-axis. So what I'm going to do is I'm going to pick a particular point x, and let's assume that this is its associated y value xy. And then let's assume we choose the opposite value of x, so same distance on the x-axis, and go up to its y value. If that is the same exact y value, just the opposite y value, so i.e. these distances are the same, then we say that this curve has origin symmetry. That is, if x is related to y, and minus x is related to minus y. So if you pick a point xy and minus x minus y also belongs to the relation, then we say that that is indeed origin symmetry relation. So let's look at an algebraic relationship to sort of see how to show that in the algebraic world. So let's say that x is related to y if y is equal to x cubed plus x divided by x squared plus 1. Does this have origin symmetry? So what we're going to do is we're going to see if minus x is related to the point minus y. So if we plug in minus x into this relation, we're going to have minus x, the quantity cubed, plus minus x, all divided by minus x, the quantity squared, plus 1. So this is the minus x value. We just need to show it's equal to the minus of that. And let's see if it is. So when we cube minus 1, that's negative 1 times negative 1 times negative 1, that's going to be equal to minus 1 times the positive x cubed, and then a positive times a negative is going to be a negative number, and then a negative times a negative is a positive, so that's going to be equal to positive x squared plus 1. Notice that I can factor out a negative 1 out of the top-hand side, giving us x cubed plus 1x all over x squared plus 1, and we know that that's the same as minus x cubed plus x all over x squared plus 1. Those are the same. But notice that that is precisely equal to minus the definition of y. So notice that if x is related to y via that particular relation, and we plug in negative x into this relation, it gives us the opposite of the original point, which means that minus x is related to minus y. Therefore, this particular relation has origin symmetry. Right? And that is a very, very interesting thing. So let's just mention just a couple side notes. So if R has origin symmetry and the domain of R is equal to the set of real numbers, then the point 0, 0 must belong to the relation. Okay? So if the domain of a relation is the set of real numbers, then the origin will always be an element of that particular relation. So if we sort of look at the original relation that we did just a second ago, i.e. y is equal to x cubed plus x divided by x squared plus 1, and if we plug in 0 for the relation, because the 0, 0 belonging to R is just a fancy way of saying that 0 is related to 0. So if we plug in 0, we're going to have 0 cubed plus 0 all over the 0 squared plus 1, which is going to be 0 over 1, which is equal to 0. So therefore 0 is related to 0, i.e. 0, 0 belongs to the graph of that relation, which sort of supports that particular instance. All right? Now, another thing that is important to note, if a relation R does not have y-axis symmetry, x-axis symmetry, nor origin symmetry, then R is sometimes said to have no symmetry, but that's not necessarily the case. R could have 1, no symmetry at all, or symmetry with respect to other things. Let's look at just a very basic example to sort of implement that. So let's assume that we have a parabola that sort of looks like that, and let's assume that we draw a vertical line straight through its vertex, i.e. that little point there. Notice that if we look slightly to the right of this and slightly to the left of that, that is practically, or exactly is if it's drawn to scale, a mirror image. So for example, if this is the line x is equal to 3, it has x equals 3 symmetry, which is just a shifted version of x-axis symmetry. So just because, keep in mind, it doesn't have symmetry with respect to the x-axis, or symmetry with respect to the y-axis, or symmetry with respect to the origin, it does not necessarily mean it doesn't have any symmetry. It just could have symmetry with respect to other things, or it could have symmetry with respect to things that are not so obvious. For example, if I were to draw, for example, that graph, you might think that that graph does not have any symmetry at all. Well, maybe not in its domain, maybe we could transform it and see some symmetry in other domains, but that's a little bit more of an advanced topic that we'll definitely introduce a little bit later. But those are some of the basic examples and properties associated to functions and relations, in particular domain, range, codomain, symmetry, and a couple other things that we also talked about as well. So I hope you enjoyed this video, and I'll see you in the next one. Take care.